Hello, ladies and gentlemen, and welcome to Mr. Saucedo's YouTube videos. Today, we're going to be talking about how elements and compounds react with one another, which sounds like it would be an awful lot of chemistry, and this is, still a little bit of biochem stuff we throw in just to make sure you're on your toes, right? So, chemical reactions, what are they? They are processes that transform one set of chemicals into another. Now, remember, we already talked about the law of conservation of matter in bio. And so realize that there is no new stuff that's being manufactured. It's just recycled old stuff. So if we have, a couple of carbon atoms, that means that our product is going to have a couple of carbon atoms in it. We're not, turning them into different elements or something weird like that. We're not talking about like nuclear processes, any of that kind of stuff. We're just talking about very simple chemical reactions. So something you need to be aware of. Reactants are the substances that enter a chemical reaction. So just picture a door. Reactants are what are going in, and they appear on the left side of the actual chemical equation. Products, on the other hand, are what are leaving that door. So they are on the right side, and they are the ones that are, the things you produce in a chemical reaction. So again, think about this. You have your reactants, little Lego blocks, and I can make this gigantic tower. And then I could easily take my product and break it back apart into its pieces again, right? So the reactants are always on the left, the product is always on the right. But just like the law of conservation, these little parts are conserved, so I can easily reverse that process and disassemble my little Lego block tower. So here's an important example. We've got glucose plus oxygen gives you CO2 and H2O. This is not balanced. That's not the point of this. I just want you to be able to identify reactants are on this side, products are on that side. Notice there's a double-sided arrow. That means that this reaction is reversible, meaning that these two things can combine to make this, or these two things can be, once they're made, basically disassembled or recombined to make the original reactants again. Now, chemical reactions release and absorb energy, or I guess I should say chemical reactions can release and or absorb energy, but still, you get the point. So we have two different types of chemical reactions here. We have exothermic ones, which are reactions that release energy. Exo means outside. There are probably a bunch of words you can think of that have the word ex or exo in them. I guess I just used one. Exit, like to exit a building is to leave, to go outside, right? Exoskeleton, bugs have exoskeletons. That means that their skeleton is external, it's on the outside. Oh, external. There you go. That's one. Exo, external, ex. Therm means heat, which is where we get the word thermometer from, thermo, thermos, stuff like that. So this means that reactants have more energy and products have less energy. So think about this, right? Again, it's kind of like the law of conservation of matter, but now we're kind of talking about the law of conservation of energy, right? So picture this. You've got a certain amount of energy that's inside of your reactants, and then you're releasing energy. So that energy is now leaving whatever you're looking at. That means your products are going to have less energy, right? So if this has a lot and this has, this energy is leaving, the result is going to be a little bit of energy, a little bit in your products. And so exothermic reactions tend to start with high potential energy and then end with low potential energy. Now, opposite, endothermic reactions. They absorb energy, and the energy that we're talking about specifically is the form of heat. So it absorbs heat. Endo, again, there are a lot of words that have the word endo in them. Again, an endoskeleton is the opposite of an exoskeleton. It's what you have, where your bones are inside of your body. But again, just plenty of root words with the word endo in there. So what does this mean? This means reactants have less energy. So again, picture law of conservation again, right? Except we're looking at energy. If your reactants have a little bit of energy and now you're absorbing more, now you're taking in energy, that means your products are going to have more energy at the end. And so again, notice it's the inverse of this graph. You've got reactants here with a little bit of energy, it's absorbing some energy, and now you've got products with more energy. So again, low reactant potential energy, high product potential energy. So no chemical reaction really happens without some input of energy, regardless if it's exothermic or endothermic. And if you want to know why, Take chemistry. There's a whole branch of chem called thermochemistry that deals with this kind of stuff. But the amount of energy that you need to start a chemical reaction is called the activation energy, or capital E little a. So E sub a is activation energy, or literally what this means is energy of activation. So it's like pushing a boulder or a ball up a hill, right? So let's say, you are expending energy. So I'm expending energy, I'm moving this up, 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 up. When it hits the top of the hill, it's going to automatically travel all the way down. All right, graphing time. 2 graphs. Boom. Label 1 energy, label the bottom part time. Graph 1. Copy that down and let's label it. I've got my reactants over here on the left. I've got my products over here on the right. I've got my activation energy, which is this little hill that I have to climb in order to get my reaction to happen. And then I also should point out, this is what an exothermic reaction graph looks like, right? Graph 2, reactants on the left, products on the right. Activation energy is this huge thing. This is what we call an endothermic reaction. Boom, we have a demo, but you're not in class, so. Last but not least, catalysts. So catalysts speed up chemical reactions. They make reactions happen faster, but the way they work is they lower that activation energy. So that little hill that we had starts to shrink. And so picture this, right? You're pushing a boulder up a hill. What if I have the height of the hill? You're going to be able to get that ball over there a lot faster, aren't you? And so when you lower the activation energy, that means that your reaction is easier and more likely to happen. So that's why it speeds up. It's not anything in particular other than by doing this process, you now make it more likely for your reaction to occur because it takes less energy. Now, something you need to be aware of, enzymes are biological catalysts. So even though we use the word catalyst to mean anything that speeds up a chemical reaction, enzymes are used purely in living things. So enzymes are only biological in nature. Now, almost all enzymes are proteins. Now, if you would have asked us 30 or 40 years ago, then we would have said, yeah, all enzymes are definitely proteins. But now we found things that are not proteins that are enzymes that speed up chemical reactions. So notice what we have here, right? We've got reactants and products, but now we've got a smaller hill. This would be our catalyst. This would be our catalyst changing the height of that. And so most enzymes end in ACE, and they normally tell you what they are breaking apart. So anytime you see something that ends in ACE and it's biological, chances are it's going to be the name of an enzyme. There are a few exceptions to that, but we won't really talk about that. So lipase breaks apart lipids. Makes sense, right? Because lipid, ACE telling you that it's an enzyme, so it's breaking something apart or building something. Because enzymes are proteins, they can also denature though. So proteins are, well, we'll talk about what proteins are later on. I don't want to give that away either. When we say denature though, what we're talking about is they can change their shape. And when they change their shape, they sometimes no longer work anymore. So what can denature a protein? What can denature an enzyme? Temperature can do that, if it's too hot or too cold, and pH, whether it's an acid or a base, that can definitely have an effect. So glucase, that's not actually what it's called, but think about it, right? If I said, hey, I have found this new enzyme, I'm calling it glucase, what do you think it breaks apart? It break apart glucose, just something like that. So for example, normal body temperature is 37 degrees Celsius. Some enzymes will stop working when you have a fever. So some of your enzymes will either get, let's say less effective. Let's use that word, less effective, which is like being denatured. And normally though, they go back to normal when your body temperature returns to normal. Another one, your stomach has a pH between 1.5 to 3.5. And so pepsin is an example of an enzyme that doesn't end in ACE, but it doesn't work in high pH places. So pepsin breaks apart protein. Specifically, it's peptide bonds that it breaks, so maybe that's where pepsin gets its name, but it doesn't work in high pH places like your small intestine. Here is a very gross little cartoon. Each one of these little squirt bottles is an enzyme. And then how do enzymes work? Last but not least, right? An enzyme structure only allows one type of reactant to bind to itself. So here I've got my substrate, here I've got my enzyme, and then right here is my active site, which is where this little substrate binds. Notice it has a very particular shape so that only this would ever fit here. Something with a different shape would never be able to match the exact little outline of this active site. Like it says, reactants in enzymes, we call those substrates. Active sites are the region where the substrate attaches to the enzyme. And then, like it says, how many of you have ever played this game before? So if you've never played this game, it's called Perfection, right? But the goal is that there are little boxes with imprints that only fit one shape. And your goal is to pour these out on a table, and you have only a limited amount of time to put all of these little shapes where they go. That's kind of what enzymes are like. So picture this little box as being an enzyme, and each one of these is a substrate, a different substrate that only fits in one of these boxes. So you can picture that the second it binds, like that little imprint, that would be the active site. When it binds to it, that would mean your enzyme's working and that you're able to, do whatever you need to do, either breaking your stuff apart or building something. Now, after the substrate binds to your active site, we call that an enzyme substrate complex. And so what it normally does is it will weaken a bond, or if it's doing the opposite, if instead of breaking something apart, it's building something, it will get two halves of something close enough that it will be able to form a bond really easily. And like it says, it lowers the activation energy, in this case, weakening the bonds until you make your products. And so this diagram is what you need to copy down in your notes. And then that's it. So if you have any questions, feel free to let me know.